If the metallurgy of a high-speed train's wheels is flawed, if the steel contains microscopic fractures because the basic forging process was, well, misunderstood, the entire network is going to derail.
Yeah, absolutely. The foundation is everything.
Right. The most elegant multi-billion-dollar signaling system in the world. It just cannot save a train with shattered wheels. Welcome to The Debate. Today, we are examining the foundational philosophy of modern .NET application design, specifically looking at how senior technical talent should approach system architecture when the stakes are at their absolute highest.
And it's a critical conversation, especially, considering how the landscape of enterprise software has evolved recently. We are looking at a very specific tension today.
Exactly. The core question we are debating, which comes directly from the scenario-based architectural expectations for modern .NET 10 engineers, is this. In modern enterprise .NET development, should our default posture be highly abstracted distributed architectures? Leveraging specialized frameworks like microservices, CQRS, and persistent job runners.
Or, on the flip side, should the default be streamlined native constructs like modular monoliths and native-hosted services built on a rigorous foundational mastery of C# runtime mechanics?
Right, and I will argue that the sheer scale and complexity of modern enterprise applications fundamentally necessitate embracing robust, distributed architectural patterns and comprehensive frameworks like Hangfire and CQRS to achieve true scalability and resilience.
And I will argue that over-relying on distributed abstractions often results in what we might call resume-driven design. I believe that true system resilience doesn't come from bolting on third-party frameworks. It actually stems from native, in-process simplicity and a deep, uncompromising mastery of C# runtime fundamentals.
Let's start right at the macro level, system architecture and how we manage domain complexity. The modern enterprise environment is really defined by its need for distributed resilience. To handle organizational and technical scale, I believe we have to utilize specialized tools.
Even if those tools introduce massive overhead right out of the gate?
Well, let's look at CQRS, Command Query Responsibility Segregation. For those who might not be, deep in the weeds on this, CQRS is the architectural pattern of completely separating your read models from your write models. Teams often implement this in .NET using a library like Mediator to decouple those commands in process.
Sure. Mediator is very popular for that.
Right. And this solves a very real, very painful problem. If you have an e-commerce system where the read volume, people browsing products, outpaces the write volume, people actually placing orders, by a factor of 10,000, forcing both of those operations through the exact same entity framework domain model is an architectural failure.
It can be a bottleneck, yes.
It's more than a bottleneck. You run into database locking issues, performance bottlenecks, and incredibly bloated code. You need the hard boundaries that a distributed microservice-based architecture enforces to optimize those paths independently.
I come at it from a different way. The problem is that microservices and patterns like CQRS, they are not free. In fact, they introduce immense distributed systems costs. When you take a system and split it across a network, you suddenly inherit a whole new class of problems.
But those are solvable problems.
At a high cost, you get network latency, serialization overhead, eventual consistency, and a massive observability burden. Most teams simply do not need this out of the gate. They adopt CQRS on a straightforward CRUD service where they are just creating, reading, updating, and deleting records, and they call it clean architecture, when all they've really done is add unnecessary indirection.
Well, I wouldn't say it's unnecessary.
My stance is that the default should be a modular monolith. You establish clear, strict module boundaries inside one single deployable application. You can use internal namespaces or separate projects within your .NET solution to enforce those boundaries. You get the logical separation, but you avoid the network tax.
I see why you think that, but let me give you a different perspective on the modular monolith. In theory, it sounds perfectly disciplined. It sounds like a beautifully organized library. In practice, though, without the hard physical boundary of a network layer, those in-process boundaries almost always degrade.
Only if you lack discipline on the team.
Developers are under constant deadline pressure. Because everything is running in the exact same memory space, it is incredibly easy, tempting really, to bypass an interface and just inject another module's repository directly into your service to grab the data you need quickly. Suddenly, your beautifully bounded contexts are a tightly coupled mess of spaghetti code.
Yeah, but
Microservices enforce discipline mechanically because you literally cannot bypass the network. And regarding CQRS, yes, adding it to a simple CRUD app is overkill. But enterprise domains are rarely simple.
True. Domains can be complex.
Exactly. When a write operation requires complex and variant validation against a normalized SQL schema, and a read operation just needs a lightning-fast, flattened projection optimized for a UI dashboard, trying to unify that into one model creates terrible, unmaintainable code. CQRS lets us optimize the write path for data integrity and the read path for sheer speed.
But you don't need a network boundary to enforce discipline. You need proper code review and architectural fitness functions. You can write unit tests that literally fail the build if one module references another incorrectly. Giving a team that struggles with internal module boundaries a microservice architecture is like trying to fix a leaky pipe by exponentially increasing the water pressure.
That's a bit of an exaggeration, isn't it?
not at all. You haven't fixed the routing. You've just made the failure mode catastrophic. In a monolith, a method call either succeeds or it throws an exception immediately. It is binary. In a microservices architecture, a network call might succeed, it might fail, or it might just hang indefinitely because of a transient network blip.
Which is why we have resilience patterns.
Right. And now, to handle that, you have to engineer retries, circuit breakers, and complex saga patterns for distributed transactions. You've traded a solvable organizational problem for a deeply complex distributed systems problem.
Which is exactly why the network fragmentation naturally forces a system to rely heavily on background asynchronous workflows. Because we live in a distributed world, the way we process background work has to be equally robust. This is why I advocate so heavily for comprehensive frameworks like Hangfire or Quartz.net in the .NET ecosystem.
Okay, let's talk about background jobs.
Background jobs require persistent storage, whether that's SQL Server or Redis. They require built-in automatic retries, exponential backoff, and visual UI dashboards so operations teams can actually see what's stuck in the queue. Let's get into the mechanics. Think about a Kubernetes environment.
Sure.
What happens when Kubernetes needs to scale down or restart a pod? It sends a SIGTERM signal, a request for graceful shutdown. If you are only using native in-memory background services, how do you handle a Kubernetes SIGTERM without dropping in-flight tasks and losing data forever?
I'm sorry, but I just don't buy that. Let me tell you why. Mechanically, ASP.NET Core's native background service is perfectly sufficient for the vast majority of continuous polling or message queue consumption tasks. Let's look at that SIGTERM scenario.
Okay, walk me through it.
When Kubernetes sends a SIGTERM, it doesn't just instantly execute your process. It signals the iHost application lifetime interface in .NET, which in turn triggers the cancellation token that gets passed into your execute async method.
Right, the cancellation token.
Exactly. If you've written your native hosted service correctly, your while loop is constantly monitoring that stopping token. When it flips to canceled, you stop accepting new work from the queue. You finish the specific task you are currently processing within the Kubernetes grace period, and you exit cleanly. You don't need a massive, database-backed third-party framework to achieve a graceful shutdown if you just understand how the cancellation token propagates through the runtime.
That assumes your processing always finishes within the Kubernetes grace period, which is typically configured to about 30 seconds. What if you're generating a massive, resource-intensive end-of-month financial report?
Well, you shouldn't be doing that in a single transaction anyway.
But what if you are processing a batch of 10,000 payment reconciliations? If that pod dies at second 31 and you're using an in-memory iHosted service, that job is gone. The state is lost. You have a partially generated report and no automated way to resume it.
I see where you're going with this.
With a framework like Hangfire, the job state and parameters are durably persisted in the database before execution begins. When a new pod spins up, it automatically queries the database, picks up the orphan job, and resumes processing. Furthermore, if a job fails because the database is temporarily offline, Hangfire automatically retries it with exponential backoff. If you're building native services, you have to manually write all of that persistence, state management, and retry logic from scratch. Why reinvent the wheel when the ecosystem provides a battle-tested abstraction?
Because relying blindly on that battle-tested abstraction often masks fundamental design flaws, and frankly, this is the exact scenario that separates senior engineering talent from the rest. If you're listening to this and you've ever stared at a distributed tracing dashboard at 3 a.m. wondering why your entire system is timing out, you know exactly what I'm talking about.
Okay, give me an example.
Imagine your background job processor is 2 million messages behind. The knee-jerk reaction, which frameworks like Hangfire make dangerously easy, is just to spin up more worker instances. Add more pods. But if your downstream SQL database is the actual bottleneck, scaling the consumers carelessly only exacerbates the problem.
Well, yeah, you'll hit connection limits.
Exactly. You will immediately exhaust the database connection pool, the database will start rejecting connections, and you will take down the entire production system. Instead of relying on a framework's magic retries, a senior engineer looks at the native mechanics. You make the message handling idempotent, meaning it can be processed multiple times safely.
Right, item potency is key.
You batch the database operations. You rely on actual enterprise message brokers like Kafka or RabbitMQ, consumed cleanly by a lightweight native background service. And let's be clear about recurring tasks. Multi-instance deployments of naive timer-based native services do break without distributed locks, yes. But leaning on a heavy SQL-backed job framework just to run a simple nightly cleanup task adds incredible latency and unnecessary database contention.
Okay, but we need to talk about how these services, whether they are background workers or public API endpoints, actually get the resources they need to do their jobs. And this brings us to the dependency injection container. The DI container in .NET is, in my view, a masterpiece of abstraction.
It is powerful, I'll give you that.
By defining service lifetimes as transient, scoped, or singleton, we elegantly manage state across the entire application. Just for a quick baseline, transient gives you a new instance every time, scoped gives you one instance per HTTP request, and singleton gives you one instance for the entire life of the application.
Standard DI lifetimes, yep.
This elegant abstraction enables foundational patterns like the unit of work and the repository pattern. Developers can inject their data access layer into their business logic without having to manually pass database connection strings or context objects down through 10 layers of methods. The DI container handles the lifecycle, it handles the disposal of resources, and it allows the developer to focus purely on business logic.
The DI container is incredibly powerful, yes, but that abstraction is exactly where the most dangerous framework magic happens. Because developers trust the container to automatically manage state, they completely stop thinking about object lifecycles in memory. And that leads directly to the captive dependency anti-pattern, which is perhaps one of the most fatal mistakes a .NET developer can make.
Wait, let me make sure I understand the precise mechanics of what you're arguing here regarding the captive dependency. Are you saying the garbage collector is completely blind to the trapped service because the singleton is indefinitely holding the reference, even if the original HTTP request that triggered the work is long gone?
Exactly. That is precisely the mechanism. Let's break it down. Suppose a developer creates a background service, which is a singleton by definition. It runs forever. Inside that singleton, they use constructor injection to bring in an entity framework application database context, which is a scoped service meant to live only for a single HTTP request.
Right.
Because the singleton holds that reference forever, the garbage collector can never clean it up. The scoped DB context is now captive. This is catastrophic in production. First, DB context is explicitly not thread-safe. If your background service is processing multiple things concurrently, you will get immediate thread safety exceptions.
Yeah, EF Core doesn't like concurrent threads on the same context.
Not at all. Second, EF Core has a first-level cache. Because the context is never disposed, that cache never clears, meaning your background service will continuously read stale, outdated data. And worst of all, the Entity Framework Change Tracker, which monitors objects for updates, will grow infinitely. It will track every single entity you ever query until you get a fatal out-of-memory exception that brings down the entire Kubernetes pod.
But the container typically catches that. If scope validation is enabled, which is the default behavior in the .NET development environment, The application will literally throw an invalid operation exception right at startup before it even runs.
In the development environment, yes. But if the team hasn't written comprehensive integration tests, or if they are manually manipulating iService scope incorrectly, it absolutely slips into production. To fix it, a developer must deeply understand the iService scope factory. They have to manually inject the factory, manually call create scope within their background while loop, resolve the scope to database context from that specific scope, and ensure it gets disposed at the end of the iteration using a using statement. You simply cannot just blindly rely on the container to do the thinking for you. You have to understand memory life cycles.
That's an interesting point, though I would frame it differently. Yes, captive dependencies are known and dangerous pitfall, but they are ultimately an implementation error. They are a mistake, not a fundamental flaw in the architectural pattern itself.
But they are facilitated by the abstraction.
Perhaps, but the common language runtime, the CLR, and the garbage collector are highly optimized engines. They handle low-level memory allocation and deallocation specifically so that we don't have to spend all day writing manual memory management code like we're in C++. I would much rather my senior engineers spend their limited mental energy on high-level API design and system robustness.
What kind of high-level design?
For instance, designing a REST API properly. If a client sends a POST request to trigger a massive, long-running batch job, the API should not block the thread and make the client wait 5 minutes. It should return an HTTP 202 accepted status code immediately, along with a location header pointing to a status endpoint, rather than sitting there and eventually returning a 200 OK or timing out. Understanding architectural design patterns, like when to use a strategy pattern to swap out billing providers, or an observer pattern for event-driven architectures, and understanding proper HTTP semantics, that matters far more to the scalability of an enterprise system than hyperfixating on micro-optimizations inside the DI container.
That's a compelling argument, but have you considered that ignoring the underlying runtime behavior will actively, predictably destroy your high-level architecture the second it comes under load? You mentioned that the CLR and the GC handle memory, so we don't have to. I have to say that is a profoundly dangerous mindset for a senior .NET developer.
How so?
Let's look at C# language fundamentals, specifically asynchronous programming, the async and await keywords. Suppose a developer writes a brilliant, architecturally pure REST API endpoint, but somewhere deep in the call stack, maybe inside a repository method, they decide they don't want to use await on a task. Instead, they call .result or .wait.
Well, everyone knows that's a bad practice. It blocks the execution thread synchronously.
Yes, but why does it matter at a macro architectural level? Why does a single .result take down a microservice? Under light testing load, it works perfectly fine, but .NET operates using a thread pool, which has a finite number of worker threads available to handle incoming HTTP requests.
Right, the thread pool starvation issue.
Exactly. When you call .result, you are taking one of those precious worker threads and freezing it in place while it waits for network I/O from the database. It can do absolutely no other work. Under heavy traffic, 100 concurrent requests come in, they all hit that .result call, and suddenly 100 threads are frozen. The thread pool starves. Your CPU might be sitting at 5% utilization, virtually idle, but your beautifully designed API is completely timing out and failing because there are literally no threads left to accept incoming requests.
It is a devastating failure mode, I agree.
Or consider the use of async void. If a developer uses async void anywhere outside of a specific UI event handler, they have created an uncatchable fire and forget missile. If an exception is thrown inside an async void method, it isn't captured on a returned task object. It gets raised directly on the synchronization context, bypassing all your global exception handling middleware and immediately crashes the entire host process. No elegant microservice architecture, no perfectly implemented strategy pattern can save an application that violently terminates its own process due to an unobserved exception.
I completely agree that asynchronous fundamentals are critical. The concept of async all the way down is a non-negotiable rule in modern .NET development. But I think you are over-indexing on localized code-level mistakes to invalidate the necessity of higher-level abstractions.
I wouldn't call thread pool starvation localized.
Fair. But let's take data access and performance optimization as a prime example. Yes, a developer needs to understand link-deferred execution. They need to know that if they attach a .where clause,
and then enumerate the query twice by calling .toList twice. They are hitting the database twice. That's the classic N+1 query problem.
Right, a very common mistake.
But once they master that, they still have to solve macro-level distributed performance issues. Take a high-traffic API that relies on a caching layer. Imagine a scenario where a highly demanded resource, like a homepage product catalog, expires in the cache. In that exact millisecond, 200 concurrent requests come in. They all miss the cache simultaneously, and all 200 requests instantly query the backend database.
Right, the classic cache stampede or the thundering herd problem.
Exactly, a thundering herd. It will crush your SQL Server instantly. Now, if you're only relying on raw C# fundamentals, you have to manually write a deeply complex synchronization mechanism. You're writing semaphore slim locks or concurrent dictionaries to guarantee that only the very first request queries the database, while the other 199 requests are forced to wait for the cache to populate. It's incredibly error-prone.
It is tricky to get right, yes.
But in .NET 9 and 10, if you leverage the abstracted ecosystem, you just use hybrid cache. It has built-in stampede protection, it seamlessly handles the locking for you, and it manages distributed caching across a Redis cluster and your local in-memory tier simultaneously. My point here is that these abstractions exist because these enterprise problems are already solved problems. We shouldn't be writing raw thread locks in our API controllers. We should be orchestrating robust, proven frameworks so we can focus on delivering business value.
And I am certainly not suggesting we write raw thread locks in our controllers. I am suggesting that if you use an abstraction like hybrid cache without understanding how it handles memory under the hood, you will still fail at scale.
Okay, explain how.
Let's talk about memory pressure, which is something abstractions just can't hide. Imagine a hot path in your application, a loop executing tens of thousands of times a second. If a developer inside that loop is carelessly boxing value types, meaning they are taking a lightweight stack-allocated struct, like an integer, and assigning it to an object or an interface type, they are forcing the .NET runtime to wrap that integer in an object and allocate it on the heap.
Creating garbage.
Massive amounts of garbage. Under extreme load, this creates continuous garbage collector pressure. The GC eventually has to run a Generation 2 collection, which literally pauses the entire application execution to clean up all those boxed objects. Your beautiful hybrid cache and perfectly orchestrated microservice architecture will suddenly experience massive, inexplicable latency spikes. You'll be staring at your distributed tracing dashboards, trying to figure out why the network is so slow, when in reality, your application is literally pausing itself over and over to clean up garbage. No amount of distributed Redis caching can save an application built on a poor understanding of memory allocation.
But that is exactly why we use profiling tools, right? We run load tests, we profile the hot paths, we identify the specific boxing allocations, and we fix them. We don't throw away the immense benefits of an entire distributed architecture just because a single hot loop was boxing a value type. The architectural boundaries we've been discussing, the microservices, the CQRS model separating reads and writes, the asynchronous background messaging, they give us the structural integrity to scale the organization.
Organization scaling is important, but
It's vital. They allow 10 different development teams to work concurrently on the same massive product without stepping on each other's toes or breaking each other's code.
And I firmly maintain that the modular monolith gives you that exact same organizational scalability if you rigidly enforce your module boundaries. But it spares your operations team the nightmare of managing distributed systems. Let's look back at your CQRS example. You mentioned using it to separate read and write models.
Yeah.
If you use CQRS natively inside a monolith, you might have Entity Framework Core handling the complex write validations with domain-driven design, and you might use Dapper to execute blazing fast raw SQL queries for the read models. That is a brilliant application of the pattern.
I agree. Dapper is fantastic for reads.
But the moment you split that across a network boundary into microservices, you now have to deal with eventual consistency. The client writes a record, the API returns your elegant 202 accepted, the web application immediately redirects the user to the view page, and the record simply isn't there yet because the background message queue hasn't finished synchronizing the write database to the read database. Now to fix that, you have to engineer complex UI polling or SignalR WebSockets just to cover up the data latency introduced by your own architecture. You traded a simple atomic SQL transaction for a massive distributed state problem.
It is absolutely a trade-off, certainly, but eventual consistency is the inescapable reality of true enterprise scale. If you are building a system that requires planetary scale, or even just cross-region high availability, where a data center going down doesn't take your app offline, you cannot rely on a single monolithic SQL transaction. You have to embrace eventual consistency.
For planetary scale, sure, but not for everything.
And handling that effectively, knowing when a scenario demands a strongly consistent database read versus when a slightly stale cache read is acceptable, is exactly what defines senior engineering judgment. The .NET ecosystem provides the tools to survive this complexity. MediaR for clean in-process decoupling, Hangfire for resilient background task management, and microservices for independent team deployment. I will gladly concede that C# fundamentals are non-negotiable. You cannot build a skyscraper if you don't understand how the concrete cures. But the true power of the modern .NET ecosystem lies in its comprehensive abstractions. They are essential for managing the sheer, unavoidable complexity of enterprise scale.
And my position remains that an architecture built primarily out of highly abstracted, distributed components without a rigorous, mechanical understanding of the underlying runtime will inevitably collapse under its own weight. Simplicity, definitional precision, and native in-process mechanisms should always be the default starting point. Start with a modular monolith, use ASP.NET Core's native I-hosted service for background tasks, understand the profound difference between an asynchronous task and a physical threat.
Right.
Know exactly when your link query actually executes against the database, and know exactly whether your singleton is capturing a scoped dependency. You should only reach for the complex distributed frameworks when you have empirical, measurable proof that the native simplicity is no longer sufficient to handle the load.
I think, despite our vastly different starting points, we have actually found a strong point of convergence here. Whether you default to a highly distributed architecture or a tightly controlled native monolith, simply reciting textbook definitions is no longer sufficient.
Absolutely. Knowing the textbook definition of dependency injection means absolutely nothing if you don't know how to diagnose a captive dependency taking down your production servers at midnight.
Exactly. Scenario-based reasoning, knowing what the fault is, naming the specific trade-offs of the alternatives, and knowing precisely when and why to deviate from the standard path is the defining trait of a senior .NET developer today. It's about having the judgment to know when the business requirements actually demand the complexity of CQRS or when a simple CRUD service is exactly what the client needs.
It brings us right back to our opening metaphor. You can't just design the sweeping, macro-level signaling system of the rail network. You have to understand the metallurgy of the wheels. The macro architecture and the micro-level runtime fundamentals are inextricably linked. You cannot succeed by ignoring either one.
There is clearly so much more to explore within the .NET ecosystem, from the deep memory management of the common language runtime to the architectural heights of distributed Kubernetes deployments. The landscape is vast and endlessly fascinating. We leave it to you, the listener, to form your own conclusions on exactly where to draw the line between native simplicity and distributed complexity in your own projects.
Just make sure your wheels don't shatter when the train leaves the station.
A perfect place to leave it. Thank you for joining us on The Debate.